Thank you for the introduction and to the organizers for the kind invitation. My talk is about small-scale index theory, scalar curvature, and Gromov's simplicial norms. So let's. So first, I will give the definition of scalar curvature and discuss its classical result. That's the Lichner-Rovich theorem, and then explain Gromov's simplicial norm. It's a concept related to topological complexity, and then state our theorem. Our theorem is proved using a small scale index theory. It consists of two parts. The first part is a small scale homology and homology theory, and the second part is a index theory. Finally, we give some kernel estimate result. Okay, so first, suppose that we have a Riemannian manifold with dimension m. So we will fix this dimension number m. Then its scalar curvature is given by the following local asymptotic identity, where b this is the geodesic ball in M, in M with centered at X with radius. So from this identity, you can see that scalar curvature, it measures how far an infinitesimal ball is away from the standard Euclidean ball. So since it measures volume, so it is very flexible. And in comparison, sectional curvature, the ridge curvature, they are very rigid, which means if you impose some condition on sectional curvature and ridge curvature, usually you can obtain very strong logical or geometric results of manifold. Scalar curvature is very soft. For example, following theorem of Kasten-Warner, it asserts that for dimension greater or equal to 3, if you have a smooth function over a manifold, any smooth function, and it's negative somewhere, any point is negative, then it can be realized as scalar curvature of some metric on a compact map. So you can imagine this scalar curvature is very, very soft. You can almost arbitrarily change the scalar curvature. This flexibility also limit is not without restriction. In the history, the first result is a Lichner-Rovich theorem. So first, we give this a heterogeneous definition. A heterogeneous of a manifold M is the integration of a characteristic class where this RTM is the curvature. And so the integration of this characteristic class is a number. So A heterogeneous is a characteristic number. And the Lichner-Rovich vanishing theorem say that if M is a spin manifold, spin is a pure topological condition, and it has positive scalar curvature, then it's A hat genus be zero. Okay, so in particular, we can use this theorem. We can reverse the result and the condition. If M is spin, suppose that the A hat genus is not zero, then so we see that there is no positive is positive scalar curvature. There is no positive scalar curvature, and we have tons of examples with in spin manifold, and they have genus zero. So we have many manifolds. There's no positive scalar curvature over it. And the proof of the Lichtenrovich theorem is a single index theorem. So it says if M is a spin manifold, then we can construct something called the Dirac operator over the spinor bundle, this spinor bundle. And also spinor bundle, it has parity. So it decomposed to the positive part, the negative part. The Dirac operator okay, acts on this the both the positive part and the negative part. And it changes parity, so it takes the form of this positive part and the negative part. And we can compute its index. It's the dimension of the kernel of the positive part minus dimension of kernel of negative part. That gives the A hat genus. Okay, and then by the Lichtenrovich formula, the square of this Dirac operator, it can be written into a Faulkner Laplacian and a scalar curvature term. And this Laplacian is non-negative. So if scalar curvature is positive, then this kernel, this operator d square is invertible. So there's no kernel at all. So of course the difference is zero, and we see that the A hat genus is zero. This is the classical Lichtenrovich theorem, and we have some questions. Questions arises. So first, Lichtenrovich theorem is only for positive scalar curvature. Positive scalar curvature, then we get the A hat genus vanish. The question is, what if the infimum of scalar curvature is less than zero? So even if maybe we don't have vanishing theorem, but question is, can we still say something about this manifold? Can we still control something? The second question is more crucial. So first we introduce the A hat class. Let's go back to the definition of A hat genus. So this A hat class is is just the integrand class in A hat genus. This this integrand, we call it A hat. And actually, this class it's not only the top degree class. It has many components. It can be written into every term is of degree is multiple degree of multiple of four. So this A hat I is the S degree component. And every term it is a polynomial of the tracking. And in particular, the A hat genus is the integration of A hat class. So it is only the integration of the highest degree term. or we can write it into the cap product with the this is the bracket means the fundamental class of this manifold. It is the top homology class. This mental class is in H lower. And so our next question, in general, if we consider a hat, but is the not necessarily top term, it's cap product with M. Okay, it's in H lower degree. This is in M minus I's homology class. This is a so all these lower degree terms, we control them. Can we say something about those homology classes? So to control a homology, so of course we need a norm. Well, one norm is that for next that is Gromov's simplicial norm. So suppose that we have any homology class, and this homology class alpha, it can be written as the sum of simplices, where every this I is a higher dimensional triangle, and AI is a coefficient in real number, if you want. And Gromov's simplicial norm is defined as the infimum of this absolute value, these coefficients. The infimum is taken over all the singular cycles representing. So basically, this simplicial norm it measures the infimum number of simplices you need to represent this. I'd like to give a simple example. So let's consider S1, that's a circle. Consider a circle here. Its simplicial norm is zero because we can construct a simplex, for example, start from this point and rotate like 100 times and go back to the same point. Okay, so this simplex represents 100 times the fundamental class. Or this fundamental class S1 is 1 over 100, this simplex. And clearly you can make this number arbitrarily small so that the coefficients, the infimum is zero. And from this example, you can also see that completion norm, we call it a norm, but it is actually a terminal. It's not. Well, in comparison, Thurston and Gromov had the following result. So there is a constant, universal constant C, which depends only on the dimension, such that if M is a hyperbolic manifold with constant sectional curvature minus, then the fundamental class, its simplicial norm is to a constant, just the volume of the. In particular, it's not zero. Paired with S1 case, we can say that hyperbolic manifolds reach a topological complex. Okay, is Gromov's simplicial norm. And now we can state our main result. Gromov's norm is what we want to control. And this main theorem is says when M is a spherical matrix, which means its universal covering is contractible, then we have the following result where this we call that this A hat minus K, it is H minus K is the cohomology and product with the fundamental mental part. This is in HK, it's in case homology. And its Gromov simplicial norm can be controlled by the right-hand side, so it has several terms. First, it is the infimum of scalar curvature is absolute value. So this we the infimum could be negative. This generalize the Lichner-Rovich theorem, and those these other terms, this volume one ball, it is the supremum of you choose the arbitrary point over the universal covering and choose radius one ball and choose volume. So volume of one ball and volume of the manifold. This ID term, it is the Dirichlet isoperimetric constant of this unit one ball. It is defined as follows. So if you have suppose that this is our the 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 unit ball and take take sigma take sigma take a lower dimensional for sigma and compute the area of this sigma and the volume of the sigma. Suppose that is the left part. So it's the area of this part, this only the boundary of sigma over the volume. So basically, we want this number to be not very small. So it says we want to avoid such a long neck structure. So this graph, if this is a long neck, the volume of sigma is big, but the area of boundary is small. So we want to avoid. Okay. And this result, it features a C0 bound, which means if you take sequence in convergence in C0 way, you still have this bound because so first the volume and the volume of one ball and this isoperimetric constant, they are C0 and the scalar curvature lower bound is also C0. This is the result of Gromov's result. This the scalar curvature is greater than actually Gromov's result is much more general. It generalized to a lower bound with a continuous function. Lower bound is zero. Here we only need a constant lower bound. It's C0. So put together all this, we see that this bound is a C0 bound. And compared with previous results, which depends probably on ridge curvature or sectional curvature, so this is an improvement. Okay, so let's summarize this result. It says the simplicial norm of the A hat class, of course, the Poincaré dual of the A hat class can be controlled by three terms. The first one is scalar curvature, the macroscopic scalar curvature. That's the volume of this one ball. This is this volume of one ball of the universal covering. It's called macroscopic scalar curvature. Because if we go back to the definition of scalar curvature, so scalar curvature measures the deviation of the infinitesimal ball from the Euclidean one. And this one, radius one, so it is a macroscopic counterpart of scalar curvature. That's why we call it scopic scalar curvature. So in this result, it has macroscopic scalar curvature, volume, and parametric constant. Basically, we have three parts. And the question is that I think most of us will agree that this bond, the scalar curvature term should be there. And the volume of the manifold also should be there. But this isoparametric constant term, can we remove this term? Is this term redundant? Okay. In general, I don't know the answer. The For two special cases, we have, yeah, we know. If k is k is zero, this m minus k is just m, and this top a hat class cap product is just the a hat genus. So this oh, Gromov norm now becomes the absolute value of a hat genus. And this is the previous result by the with together with Jimmy Wang and Bo Zhu, we construct examples such that to show that we cannot remove this isometric constant term. So, so this inequality is incorrect. You only take scalar curvature, not controlled only by scalar curvature and volume of the not. It's incorrect. We cannot remove the but for another extremal case, k is not zero, k is m. Okay, this product m minus m, that's zero. And we go back to first second page. Okay, so the lowest degree part A hat is number one. The one cap product with the one, this one cap product with fundamental is still the fundamental class itself. So, and this fundamental class, its Gromov norm, sometimes also referred to as Simplicial volume. And a result by Goose, Brown, Sauer that this simplicial norm can be controlled by macroscopic scalar curvature and the volume. Yeah, they proved the following result. Simplicial norm can be controlled by a constant only depending on the macroscopic scalar curvature multiplying the volume. So there is no isoperimetric constant here. And a question is when k is zero, the lowest, we need isoperimetric constant. When k is m, the top case, we don't need isoperimetric constant. So a question is who is special? M is special, zero is special. So the first case is one if k equals m is special. Okay, so just k equals 0, 1, 2, 3 until m. All this, only m is special. So this all this 0 to m minus 1 and m minus 4, we need isoperimetric constant. So our result, together with Goose and Brown-Sawa, together gives an optimal result. But probably case 2, case 0 is special. Okay, so that means except 0, so k is k from 0, 1, 2. So 0, only 0 is special. So 0, we need isoperimetric constant. From 1 to m, we don't need, so no isoperimetric constant. Then our result can be significantly improved. And I'm not sure which this is correct. And maybe this is a question I'll leave to the expert here. Okay, so now we move to the proof of this theorem. Is small scale index theory. So first, let's start with the homology and cohomology theory. So let's first denote the fundamental class of M by gamma. And for any epsilon greater than 0, we let this cochain complex be the space of gamma invariant continuous functions. Delta, this is a universal covering. And we have k plus 1 copies. So gamma invariant means so, so you have a copies 0. Gamma invariant means for to pick up any gamma from the fundamental group. This phi x0 to xk, it is equal to phi x0 gamma to gamma xk. It is a diagonal action to the k plus 1 copies. And we want the functions to be supported on the epsilon diagonal. Epsilon diagonal means it's supported over the set x0, xk, such that pick up any I and j, the distance between xi and xj is less or equal to epsilon. Near the diagonal, we call this epsilon diagonal. And the co-boundary map on this cochain complex is defined as follows. And you can see that this formula is very much like the definition of cohomology, the co-boundary of cohomology, except that here we only work on the vertices, not the whole complex. This blue. And with this cochain complex, we can define its cohomology denoted by HK epsilon. This is what we call epsilon. Okay, and dually, we can define the homology. Homology, we use functions. Of course, homology, we shall use measures. So now let's let this C epsilon be the space of gamma invariant measures. Now the K plus one is of universal covering, also supported on the epsilon diagonal, and the boundary map can be defined via reality, where this this means we the measure and the function, they are both gamma invariant. So we only take the integration over the quotient space or over a fundamental domain. And through this, we obtain a complex, and its homology is what we call epsilon homology. This is our small scale homology and homology theory. Okay, and now we compare the singular homology with this epsilon. So the the complex of singular homology. So every singular homology, that's a finite sum AI. Every delta I is a dimensional triangle. So it is a finite sum of simplices with no risk. So implicitly there is a more condition here. There's no restriction on the size of the simplex. But the epsilon homology, first, it is a measure and be viewed as a continuous object. So it's formally an infinite sum of not the simplices. We don't need the whole simplices information. We only need the vertices. And with diameter less or equal to epsilon. So that's the condition we need the support near the epsilon near the diagonal. So formally, it is infinite sum of small simplices. And one more remark here, we only need the vertices of simplices. The question is, why not this use k plus one copies of manifold rather than this? We use the gamma quotient of universal covering. This is because okay, let's go back to the circle case again. So suppose that now you have a simplex from this point A to point B. This is a simplex, and you can construct another one from the same point, same same starting point, same terminal, but rotate one circle. If you just use vertices, you cannot distinguish them. But if you lift these two to the universal covering, so the first one, small one, is this, and the second one, so that if you use points over the universal covering, you can distinguish these two simplices with same vertices. And this small scale homology and cohomology is a quantitative version of Alexander Spanier's homology and Alexander Spanier's homology and cohomology are infinitesimal version. So let epsilon goes to zero, you get Alexander Spanier's homology. And you can imagine this is exactly the homology of the manifold, because if you use very small triangles to construct to reconstruct the homology information, yeah, you can recover information. And the key point of spherical, in our main theorem, we suppose that M is aspherical. The point is that, okay, instead of considering infinitesimal limit, when M is aspherical, you can take epsilon to be any number. This homology is always isomorphic to the homology of the matter. This is because, so first, the so the singular homology can be embedded to epsilon homology. So if you have a triangle, this triangle has vertices x0 to xk, you just send it to the delta measure, the point x0, the vertices. And the point is we need this x0 to xk to be in the epsilon diagonal. But what if x0, xk, they are not in epsilon diagonal? So we can make some barycentric subdivision, and we can divide this complex to a sum of some very small simplices, and everyone in the epsilon diagonal. And okay, similarly, send everyone to the vertices. Oh, we have such an embedding from the classical homology to epsilon homology. We can always construct, but we we want to construct a chain homotopy between them. We want another direction from epsilon homology to homology. Remember, epsilon homology are only vertices. Now you only have 0, x1, x2. How to recover a simplex from only vertices? So of course, we consider manifolds connecting. So x0, x1, you can connect them. You can connect x0 and x2. So you can always construct this one-dimensional simplex. Two-dimensional, that's this contractibility. Contractibility condition works. So because the universal covering is contractible, so of course you can construct a homotopy between this x0, x2 to x0, x1, and that is a two simplex which connects x0, x2. And you can construct via this way so that the the simplices are compactable. Means if you because you construct from lower dimension and construct lower dimension skeleton and then higher dimensional. So if you have a higher dimensional complex and consider a subset of vertices, the corresponding simplex is just a phase of the dimensional. It has this compatibility condition. And well, so now, we prove that if M is aspherical, then any epsilon homology is the classical. So next question. So Since we have isomorphism, this A hat dual, it is it is a homology class. So can we find a representation in epsilon homology of this? And that's our small scale index theorem. Small scale index theorem will give you a concrete representative. And with this representation, we can estimate its simplicial norm because, okay, so this is a mesh. Formally, just formally, we can view it as an infinite sum. Any x0, xk, those are vertices. Remember, every x0, xk, we reconstruct a simplex, and the coefficient, this is a measure. Formally, we have a weight, this point. Formally, it is such an infinite sum. Remember the definition of Gromov simplicial norm, that's the sum of this absolute value and take the sum of these coefficients. So we see that its Gromov norm can be controlled by this infinite sum, formally infinite sum. And of course, a reasonable way to make this infinite sum rigorous is to replace it by an integration. Okay, this one is rigorous. This argument can be this formal argument. We can make it rigorous using Gromov's dual principle. Okay, so at least formally we can understand it. So our task now is to find a representation and find the control the integrand function, and then we find a upper bound of the hat dual. Okay, so the small scale index theorem. So we have let's choose a old smooth function f. It takes the form of this um, -1 to 1. And with this derivative this decay function and its Fourier transform, this Fourier transforms is compactly supported. And another function g is square minus 1 fixed of. And with this, it is given by some functional calculus or Dirac operator. This seemingly complex construction is from it has a motivation from beta K theory. And since we for construction we suppose that this F and G they are all finite the Fourier transform have propagation. And the kernel of this difference idempotent also has my propagation. So it's fit into the kernel forms of fix any point x. Its support is only near a over a normalized constant small ball. And with this small scale idempotent, we can take a product this kernel. We can state our small scale index theorem. So the Poincaré dual of A hat genus is in epsilon homology. It is the following measure. First, it has the Riemannian measure over the copies of the universal covering. And the first part, this product kernel, is like a circle from x0, 0, x1, 1, x2, and go back to xk, 0. So you can take the trace of this pointwise trace, and you get a measure over the a plus one copy of universal covering. And with this representation and the following kernel estimate, not estimate, the pointwise norm, its index kernel can be controlled to a constant in terms of the infinite normal scalar curvature and the directly isoparametric constant of epsilon ball. Okay, with this we can prove our main theorem. We only need to take epsilon to be 1. So we plug this kernel estimate to this kernel expression. So you have A copies, and the final one is volume of the manifold. This can just plug in and take the integration because our integration is over the epsilon diagonal. So first, x0, it takes value for the whole set, and x1 is in epsilon diagonal. It's in epsilon neighborhood. So this gives the ball x with centered x0 and radius epsilon. So if you plug in and take the integration, you shall get our main theorem here. It explains the okay. And so this small scale index theorem, it should be viewed as a quantitative version of higher index theorem by Moscovici and Moscovici. This theorem is mainly inspired by three sources. So first, of course, that's Jones' combinative geometry. And also, this quantitative homology is from Yu's quantitative operator theory. And the index computation part is from Bismuth-Lebau's analytic localization method. And the kernel estimate, we borrow some techniques from trick analysis, Moser iteration. And one more thing is that you can take epsilon to be any number. So different numbers gives different estimates. In particular, if you take epsilon to be the injectivity radius of the manifold, you get the following bound such that so there's no isoparametric constant because inside injectivity radius the isoparametric constant has a universal lower bound. So it means the given injectivity radius lower bound, volume upper bound, and the scalar curvature lower bound, we can control its the universal the Gromov norm of Poincaré deal of any A hat different epsilon, different estimate. Now we go to the proof of the theorem. So the epsilon homology has a map. We have a morphism from the classical drum cohomology. Suppose that you have this function phi 0 to k, that epsilon cohomology, and to drum cohomology, it's a differential form point. Those v0 to vk, they are from the tangent 0. This form is given as follows. You take an alternating sum, and this v0, okay, this phi has x0 to sk variables, and this subscript x sigma 0 means it takes derivative to the sigma zeros coordinate. And in particular, if phi is given by a product function, then it has a simple expression is just the a zero and the product of d. So instead of the original theorem, we shall prove a stronger limit. So this is the small scale, the measure. It's paired with this function. We prove that when epsilon goes to zero, it is the a hat genus product with the image of this homology. With this limit, we prove the small scale index theorem. And this step is we use Bismuth-Lebau's optimization technique. And now let's see something about the kernel estimate. This universal covering, the key point is that this universal covering is in general non-compact. So it's this functional calculus, we cannot simply write it as a sum of values, eigenfunction, eigensections. So instead, this function we know that the Fourier transform had support. So we can use the finite propagation speed property of wave equation and reduce. So any point we want to estimate the kernel. So instead of the whole manifold, we can the outside region and only consider this this ball with radius 1 because it's out in -1 and 1. And this region, this unit ball, it is compact. We put everything to this compact ball, and we can consider right now the eigen section decomposition. This rock operator square, we list all its eigen sections with normalized norm 1. And it has a discrete spectrum, and we can write down functional calculus from the Lichner-Rovich formula, and together with Cartol's inequality, the norm of this eigen section, its Laplacian, we act function, is controlled by hand side. And if we plug in the Lichner-Rovich formula, replace this Laplacian by d squared minus sectional curvature. Okay, since each ui it is eigen action with respect to lambda. So this is less or equal to lambda plus. This is the step we get infimum of scalar curvature. From this inequality, you you see that you take a Laplacian, so you lift the regularity. Lift the regularity. This can be controlled up to a constant original function itself. If you iterate this procedure, you can control the infinity norm of this function. That's the And this iteration procedure is where we need the isoparametric constant. If you take a higher power, so you need this isoparametric constant, the region. Do other iteration, so you can control the infinity norm together with Peter Lee's trick. You can control the pointwise norm, a square, and plug this estimate into this functional plus is less or equal to the norm, less or equal to the sum. Then you can control the kernel. And we obtain finally, together with the small scale index theorem, we obtain our the outline of the proof. Thank you very much.
Thank you very much for your beautiful talk. Are there any questions?
But may I ask, because one of the question, of course, if you can say something in this respect that conjecturally, if you have positive scalar curvature, then simplicial volume is zero. Can you say something in this respect under additional conditions? Because positive scalar curvature should make.
You mean vanishing theorem, right?
Right. Even zero scalar curvature.
Okay, the point is, yes, so far I tried, but so far I cannot. The point is, okay, if we replace in this main theorem, let's erase this.
Are you
So
sharing?
if,
I
yes,
think you have to share the screen so we can see what you write.
okay, I'm not sharing screen. You cannot see my screen?
Does anyone see the screen?
I see the screen, but of course, you have not started the writing things, right?
I'm
Okay,
not writing, I'm not writing.
Okay, I will try.
Okay, I erased. Okay, so
Sorry.
as I said, you can replace this epsilon to be this one by epsilon by any number you want. And okay, if it's positive scalar curvature, so we can let epsilon instead of fixed epsilon, we can let epsilon go to infinity and see if it's like the Lichtenrovich proof. But the point is, if we let epsilon go to infinity, this volume grows, and this isoperimetric constant it also grows, but they compete with each other. And so far, I don't know how to control even with a probably exponential decay factor. I don't know, so I'm not sure. Yeah, because there is a numerator and denominator, they compete with each other. It's unlike the k equals to zero case. So far I cannot get a vanishing theorem.
Yes,
Thank you.
this is very much related to the strong Novikov conjecture.
Yes, yes, strong Novikov. Yes, you can see similar phenomenon, similar pattern in those questions. Strong Novikov, that's also you need to find the growth rate of a
Uh,
quantity.
I think the vanishing of the simplicial norm would, in the aspherical case, would follow from the strong Novikov conjecture if it's true. Because the simplicial norm,
Yeah, but it's slightly weaker than Novikov conjecture.
yeah, you're right. It's weaker. It's
It's
a
weaker, and therefore it may be more approachable.
yeah.
Are there other questions or comments? We can stop the recording